I am so delighted to be joined today by Professor Paul Ewart, who I got to know over the last couple of years and had the pleasure of working with a few months ago. Paul is Professor of Physics and formerly the head of Atomic and Laser Physics at Oxford University. He's a Fellow and Tutor in Physics at Worcester College at Oxford University. And you just had a very rich, interesting career in terms of exploring and researching this really interesting area of physics that I'd love for people to hear more about. So welcome today. Thanks so much for spending time with me.
Thank you, Sam. It's a pleasure to be with you.
Now, people will quickly be able to tell from your accent that you're not really from Oxford originally. So could you please tell us about your background?
Okay, yes. Just people notice almost immediately I'm not from Oxford, and they noticed that too when I first came here. Oh, you're not from around here, are you? I actually started life in Belfast many years ago now. I grew up in Belfast, went to school there, went to university there, and at the end of that time, I graduated with my PhD in physics and moved to Imperial College in London with my supervisor, who offered me a job as a postdoctoral researcher there. And that transmuted into a temporary lectureship and then a research fellowship there, after which I moved to Oxford about nearly 50 years ago. And so I've been in Oxford really for most of my working career.
You managed to keep your accent.
Yeah, I mean, apparently
That,
it's quite difficult to get rid of it. Doctors haven't found a way of doing that yet.
How did a young Paul Ewart first gain his love of physics?
That's a very difficult question. I've been asked that before, but really it's just part of me. I was just naturally interested in the world around, and when I was a young child, I was particularly fascinated with astronomy, because growing up in Northern Ireland at that time, the skies were clear, the winter nights were beautiful. You could see a whole host of stars from where I lived, and I was just fascinated by the size of the universe and wanted to know more about it. So I started reading books about planets and stars and stuff like that. And that then got me interested in basically atomic physics. And I stumbled across a book by Banish Hoffman in the school library called The Strange Story of the Quantum. And I thought, this is really weird stuff. I didn't really understand it much then, but it was really fascinating. And I was able to bluff my way using the right words. But I thought I want to understand more about this. And so, although all my friends used to laugh at me when I said I wanted to be an atomic physicist, it all worked out fine in the end. And so I've spent my life studying atomic physics, and using lasers, which was just being invented at the time I started my university career. Lasers came on the scene around then, and I was very fortunate then to be taken on by one of the leading lights in the United Kingdom in laser physics, Professor Dan Bradley, and he was the Professor of Physics at Belfast there. And he started a laser group and invited me to join him in Imperial College, and my career went on from there.
Wow, so you were there right at the really earliest days of lasers. What was that like?
Well, that was fascinating because the word laser had just been invented, really, to the acronym Light Amplification by Stimulated Emission of Radiation. And the word has gone into everyday usage now. Most people don't know what it stands for, that it is actually an acronym. But in the early days, it developed out of what was called a maser, a microwave amplifier by stimulated emission of radiation. And the seed of it all went back to Einstein, who thought of the idea of stimulated emission, that photons of light would stimulate an atom to emit another photon of the same variety. And when that happens, the two photons are exactly in step, and we call that coherent. And then those two then stimulate two more atoms to produce four photons, and so it grows exponentially, 4, 8, and so on. And so you get this immense burst of radiation with all the little waves of light all in step. And so this was a fascinating concept, and to have it realized and practiced after almost 50 years of theoretical possibility was really exciting. And so our group was one of the first groups in the country and in the world to develop light lasers whose frequency, whose wavelength, color of the light could be changed. And that was a very important step because we could then adjust the wavelength of the light coming from the laser to match the wavelength that was absorbed by atoms or molecules. And that gave us a very powerful probe of atoms that we could excite particular quantum jumps, as they're called, in atoms and molecules precisely, and study the structure of the atom. So that really got me really excited. And so I chose that for my research career.
Did you have a sense that you were turning science fiction into science fact at the time? It must have been quite a leap of the imagination, that the technology you were beginning to develop.
Well, I think things were moving so fast in those days that we didn't have time to think much about fiction. It was just fun enough without having to read fiction.
So this is the 1970s, is it? So
Yes,
obviously there's
yes, early 1970s. Yeah,
yeah. So I mean, there's great leaps happening in quantum physics anyway. It's sort of
yes,
the Richard Feynman era, isn't it?
yes, yes.
So yeah. So you were really working both in the theory and the technology, weren't you, at the same time?
Initially, I started off as experimentalist. I ended up doing a little bit of theory just because we had to, because no one else would do it for us. But I was very fortunate in being able to collaborate with some very clever theoretical physicists who helped us with the hard bits. So my own particular interest was mostly in developing new techniques using lasers and studying atoms that hadn't been studied before, and just addressing questions that previously would be very difficult. But the laser provided us with a tool to do things that were impossible before. For
So what
example,
sort of? Oh, sorry. Go ahead. Yeah.
I was
Um,
going to give you an example.
yes,
the
that's what I was going to ask for.
well, it sort of reminded me of my interest in astronomy and astrophysics because I was persuaded by my supervisor, Professor Bradley, to do this experiment that would help people understand what was going on in the atmosphere of the sun. Now, as you know, we can study the sun and stars by analyzing the light that comes from them. And so one of the issues was how does the light get out of the sun through its atmosphere to us? And the atmosphere contains all the elements, for example, like magnesium and sodium and so on. And you can see these elements in the sun's atmosphere by the light that they emit or absorb. And so one of the issues was if we could detect how magnesium atoms in the sun absorb light and then were ionized to release an electron, that created the plasma that surrounds the sun. And all the atoms in the sun's atmosphere get ionized by the radiation, and there's a kind of balance set up between the electrons coming off and then rejoining the atoms, and that creates this kind of plasma corona around the sun. So I was fascinated by being able to contribute to understanding that. But in order to do that, we had to be able to get atoms from the ground state, their normal level, up into an excited state. And then it was easier for them to be ionized by absorbing another quantum of light to become ions. And so using our lasers, we were able to take the magnesium atoms from their ground state up into their excited state, their first excited state, which lasts only a few nanoseconds. That's a thousandth of a microsecond. And so you need to get photons in there very quickly. And that's why we use our laser pulses with very high intensity. So we created these excited atoms, and then we shone another pulse of light through these atoms to see how they absorbed, and then they were ionized. And so that got me started in using lasers to study atoms and molecules.
Wow. Yeah, it must have been such an extraordinary time, being at a place like Oxford, during those days. Yeah, people who know me know that I've got a lot of interest and work in the space sector, and you've described an sort of astronomy, astrophysics experiment there. Was there a lot of work that you got to do that did cross over with astronomy or astrophysics?
Well, that work was carried out in Belfast, where there was a strong solar physics group, and so they were interested in studying other aspects of the light from the sun. But I quickly, when I moved to Imperial College, my research took on a different line because we stumbled upon other ways of studying atoms. And then it became more and more applied. So I left the astrophysics behind at that stage and got more into studying the atomic physics of how light excites the atoms and how the electrons orbit the atoms and so on. Just studying the quantum nature of the atomic structure.
Do you still have much to do with Queen's University in Belfast, or are you ever involved in? Were you ever involved in more work back there, back home?
No, once I left, I only ever went back once to attend an induction ceremony for the vice chancellor, I think, but and they had to lend me a gown because I didn't have a proper gown. So I haven't had much contact, although it would be nice to have some, but things have moved on.
Yeah, well, I have a share an affinity with you there. I've got 9 university qualifications, and I've never been to a single graduation, which is a record that I've somehow managed to maintain thus far. Which people don't understand. They're like, why wouldn't you go to the graduation? I just never got round to it. But my wife and I went to Belfast for the first time just a few months ago, and we absolutely loved it. It was a wonderful city. And
Yes,
we did go up to the Giant's Causeway and travel a bit of the coastline. Just a magnificent place, Northern Ireland. Loved it.
it
But I
is.
did get the sense of what you're saying, like the lack of light pollution. For a young person looking up at the sky, it just must have been wonderful. Did a
Yes,
young
yes.
Paul Ewart have a telescope?
Young Paul Ewart coveted a telescope, but young Paul Ewart couldn't afford one.
But did you just sort of go out and just take it all in day after day?
Yes, yes, that's right. Yes, yeah.
Yeah, wonderful.
Yeah,
Um,
it's been one of my long-time ambitions when I get a bit of time to build my own telescope, and it's still at the planning stage.
right. A great retirement project, recently
Yes,
retired. Yeah.
yes.
Well, I hope you get one. I hope you get a really big one and you get to take it to Northern Ireland or something. But given your work in atomic and laser physics, could you tell us some more of the technological applications, sort of the work you were doing? What sort of things did it end up going into?
Well, it went in two directions, Sam. The first one was in fundamental physics, that using a laser pulse, we could excite an atom into some excited states. And when the spread of wavelengths in the laser pulse was sufficiently broad, you could excite multiple levels in the atom at the same time. And the atom then got into a state where the electron, uh, as it were, was in multiple quantum levels, and they added together to give a very localized position to the electron. Instead of being a rather fuzzy cloud, as it normally is, as we think of it, it was localized in what we call a wave packet. And it began to look like a classical particle orbiting the nucleus like a little planet around the sun. And this was one of the first times this had been done, that we were then probing the boundary between quantum physics and classical physics. That my work at that stage had been exciting atoms to very high quantum states where the electron orbits a very large distance from the nucleus at a size where it could be visible in a microscope. Um, and it's funny that the electron is then orbiting the nucleus, and other atoms get between the electron and the nucleus and fill up the space between it. And yet, this electron could still wander around its orbit, even though there were 10,000 other atoms between it and the nucleus. So it was really fascinating stuff. So these were Rydberg wave packets that were localized manifestations of the electron that looked like a classical particle, and you could see the electron move in an elliptical orbit, emitting in little pulses of light as it passed the nucleus when it behaved like a real atom. But when it was further out, it looked like an ion. And so it was periodically coming in and out close to the nucleus in an elliptical orbit and sending out little pulses of light or absorbing in little pulses when it was close to the nucleus. And that was at the boundary between classical and quantum physics. And I thought that was really interesting. But other people have taken that work on, and that kind of coherent quantum optics has become a whole field on its own. I then got interested in making atoms or molecules react to 2 or 3 laser beams at once. When 2 laser beams cross, they interfere and produce a kind of interference pattern where you've got bright and dark fringes of light. Just like the famous Young slit experiment, where you shine light through 2 slits, and the light from the 2 slits are coherent, they're in phase, and so when they cross, they either add or subtract from each other, and you get a bright and dark pattern. So when you do that with 2 laser beams, we could create this bright light and dark pattern suddenly. And then what happened was the atom, the refractive index could suddenly change, and a little wave would pass out from that initial pattern, and so the pattern would sort of come and go. And when we shone a 3rd laser beam onto this little pattern, it got reflected from this little grating that was oscillating. And the speed with which the grating moved was the speed of sound. And so by looking at the oscillations in the reflection from this little pattern, we could measure the speed of sound in the gas. And that gave us the temperature. And then that opened up a whole range of applied physics where we could use our lasers to select particular molecules or atoms in a gas, particularly a hostile gas like a flame or a plasma or even an explosion. And we could detect particular molecules and measure their temperature and the pressure using the signal from the scattered laser light. And that opened up a whole phase of applied spectroscopy that allows us to study combustion, how pollutant gas is created in engines that pollutes the atmosphere. And so we were able to feed that into new engine designs to make them more efficient with the aid of industries like Jaguar Land Rover, Shell, the oil company, and British Gas, who rely on this burning process, this combustion. And so they wanted to make it cleaner and less polluting. And in order to do that, we needed to understand the fundamental processes that were going on. And this technique allowed us to do that. So my research took a very applied shift at that point in time, which was quite satisfying to find that somebody else found what you were doing interesting and useful.
Yeah, it sounds like it's been taken up in quite an important way in environmental science. That's quite fascinating. And I realize combustion and studying engines and applications for engines has been. Oh, okay. Are you with me now? Can you hear me now? Professor, can you hear me now?
Yes. You want to repeat that
Great.
question?
Oh,
yes.
Yeah, I'll ask the question again. Combustion and engines has been quite an important part of your work and the application of your research, isn't that right?
Yes.
Yeah. Was part of what you imagined it would be when you started, or was that incidental to your research?
Not at all. It wasn't. I had never intended that to happen. But when we realized that we could do something with this technique that turned out to be useful, that was very satisfying. And we were able to get a lot of industrial funding because people like Rolls-Royce and British Gas at that time and some of the oil companies were interested in reducing the pollution of their engines and fuels. And so they needed to know the fundamental physics and chemistry of what was going on. And this technique allowed them to do that. So one of the important parts of physics is to develop new ways of measuring things. And in some places, it's very difficult to measure what you want to know. And so one of the satisfying aspects of our research has been to develop new techniques to measure things that are difficult to measure otherwise.
Wow. I want to ask you about quantum physics, given how important it's been. I think people of all shapes and sizes, ages and backgrounds are fascinated confused and slightly terrified by quantum physics. Would you make your case to anyone and everyone just now why studying quantum physics is not something to be scared of and really is weird and wonderful?
Well, I can appreciate the difficulty of understanding it, and puzzled by it. I think it was Niels Bohr who said that if you're not shocked by quantum mechanics, you haven't understood it. So it really is totally upsetting in the sense that it offends our common sense idea of how we describe the world. That's how we describe things using what we call classical physics, that everything has a definite location in space and time. But when we actually get right down to study these little tiny things, we find that it isn't quite as clear cut as we had imagined. And so we're actually forced by nature itself to find a new way of describing the reality that exists at this very small length scale, the size of atoms, a thousandth of a millionth of a meter, that kind of scale. And so what we find there is matter and energy behaving in a way that's quite surprising to us. One of the most fascinating aspects for me was to get involved with a research group in Paris, where I was helping with the laser side of things, where we were able to create helium atoms in exactly the same quantum state. That means that everything about the helium atoms was identical. Normally, every atom is a little bit different because it's spinning and pointing in a different direction. And so in principle, you can tell one atom from another as they bounce off each other. Now, one of the fascinating aspects of quantum theory is that we can describe it using a set of integer numbers called quantum numbers that describe the rotation of the particle, its energy level, and so on. So you can get a complete description of the state of an atom using these quantum numbers. And if they're all identical, then it turns out that those two atoms can't occupy the same region of space. This is the Pauli exclusion principle. For certain kinds of atoms that have spin, they can't be in the same place in time. And what we were able to do was to get these helium atoms to be in exactly the same state. The little nuclei were spinning in exactly the same direction. And so everything about them was identical. Now, normally, if two helium atoms collide like that, they bounce off each other because the electrical forces stop them getting into the same space. And so they bounce off and they transfer momentum to each other. And so heat can be transferred across a gas by this collision process. But if you make the atoms totally identical, then what happens when they get to the same region of space? They just pass through each other. And it's totally a miraculous kind of effect that instead of colliding, they just pass through each other. And that's like something going through a wall, which is almost miraculous. And I mean, as a Christian, I find that incredibly interesting that here the laws of physics seem to be being disobeyed, but actually overcome by a different law that we didn't know about. And that helped me enormously, because one way of thinking about miracles is that God is able to use laws of physics that we don't know about yet to do things that would seem to be impossible. So it's very humbling, and that's one of the things that I've loved about physics, that you're probing the very essence of reality, and it really opens your imagination to possibilities that would be impossible using your common sense.
It
That was a
must
very
it
long
must be
answer.
so.
Sorry about that.
No, we like long answers here. I want you to be free to really talk through your experience. Yeah, you don't normally hear many scientists using the word miraculous. That's sort of seemed thought to be I don't know, taboo. But you're looking for regularity. But it must be so satisfying to be probing the deep structure of the universe, the deep structure of nature. Was that something that when you just go to work as a quantum physicist or an atomic or laser physicist, are you going about your business thinking, I'm probing the deep structure of nature today? Uh, does that enter into your mind when you clock in the office?
Once in a while that happens, but most of the time you're trying to solve the technical problem of the day.
Yeah,
But
can
what
imagine
you're
it.
saying is absolutely true. That's what motivates you. That's what really gets you up in the morning, because we're chipping away at the cold face here, finding out a little bit more and trying to piece it together to get a better picture of reality.
Yeah.
What we would call a critical realist view of reality. We're humbled by the limits to our knowledge here. And one of the really fascinating things about physics is that we're really pushing the boundaries of what we can know about reality, about matter and energy. And that's very humbling, but it's very exciting as well. So that's the motivation for doing this kind of stuff, as well as, of course, on the way you find out that something you've discovered can be useful to somebody else and help the general condition of mankind. So that's a bonus. So one of the really joys of doing physics is that you are trying to get to grips with reality, understand nature fully, um, and as a byproduct of that, you get things that are useful. Um, and science progresses that way by probing the boundaries and then discovering things that can be useful, whether it be in engineering or even in medicine, to help relieve suffering or to improve agriculture, to improve tackle some of the world's big problems. Um, there are two approaches to that, of course. Is you can tackle the problem head on and try to use what you know already to solve that problem, or you can try to understand things at a deeper level, and in so doing, come up with alternative answers to the problems we're facing. So I think both approaches are important. Both applied research and pure research need to be going on at the same time.
It's a continual dialogue, it seems, and an unexpected one because you don't know where the next great application is going to come from. But I mean, this is what you've described is really what this channel is about the frontiers and working on the frontiers of lots of different disciplines. And you've had such a rich experience being right on the frontier of physics and for at such an interesting time. That period in the 20th century, later 20th century, where quantum physics and lasers, they're really coming across. Is there anything that you're really excited about or you're keeping an eye on in terms of the future of physics and the disciplines you've been involved with?
I think the obvious one today, Sam, of course, is artificial intelligence, and underpinning that also related progress in quantum computing. What quantum physics has provided us with is a very powerful way of doing computations. Um, as you probably realize, most people know these days that digital computers work by using a little sequence of numbers, one and zeros, to represent numbers and quantities to do calculations. And so they're done in a series of one after the other. And they can do it very quickly and solve problems very quickly. But using quantum physics, we can do these calculations in parallel. Instead of having the little elements in either a one or a zero, they can be both at the same time. And that allows them to do calculations simultaneously, as it were, much faster. Without going into the details, this sort of quantum nature of at the atomic level allows us to do computations that are much more difficult for a conventional computer, and we can solve problems more quickly and problems that would be intractable using normal computers. And that's enormously exciting, because some of the problems that we are faced with um, will require enormous computing power. One of the kind of scary bits of it, of course, is that the physicists are now toying with the idea of getting computers to do their thinking for them, as it were, and to come up with new theories. And that's a rather strange concept. It's a bit like turkeys voting for Christmas, that we're going to be out of a job because the computers will be able to work out the theories for us. I'm not sure that's actually going to happen, because at the end of the day, they have to be understood by humans. And so that's a fascinating prospect. Development of quantum computing with its enormous potential for increased power of computing and artificial intelligence, which will enable us to do kind of theoretical and even experimental work that would be very difficult or impossible without it. So enormous steps might take place in the coming few years with the combination of quantum computing and artificial intelligence.
So it's a great time for students young and old to get involved in physics and quantum computing. I mean, obviously the applications there, you don't need much imagination to sort of realize what could happen there.
Yes.
Is anything else particularly exciting you about science or science even outside your discipline?
Well, I think those are the two things which are catching the headlines, and the applications of those in how they change our daily life are really both exciting but perhaps a little bit scary for a lot of people. And it's going to be important for scientists to um, make sure they have enough input into the decisions that are made by politicians and by leaders in our society so that these new developments are used in a helpful way for humanity and not used to improve our efficiency of destroying each other or the planet. I think some very difficult decisions are going to have to be made in how we apply the new technologies that are coming out of the new physics.
Yes, and Stephen Hawking, obviously very active in that era in a lot of similar fields, a lot of crossover. Yeah, he had some pretty stark warnings for humanity in his last two writings.
Yes.
Martin Rees has written a lot on this, and we're actually talking to him in a month or two.
Oh,
Um,
good.
do you think scientists have enough of a voice on these issues in the general public? Are people heard enough?
I think the short answer to that is probably no. um, but it's difficult to see how um, we can, as scientists, affect the ordinary man in the street, as it were, because the explaining what we're doing and uh, challenging misleading ideas that are put out by other people, especially on social media, for example. And there's an explosion of misinformation and misunderstanding. And I think it's important for scientists to do what we can to um, be honest with people and to both warn them but also reassure them that many of these misinformation and conspiracy theories are not based on real science and trustworthy science. So it's important that scientists get together and act coherently together to persuade politicians and leaders in society to listen to the truth, because science is about trying to find the truth about things as best we can. And so we should challenge misinformation coherently as a body of scientists where we can. And by and large, we've had good examples of that. One of my friends and former colleagues, Sir John Houghton, who was a professor of physics at Oxford here, and also a member of our local church. He was chair of the International Panel for Climate Change way back in the early days, who first flagged up the dangers of human-caused climate change. So that kind of input from scientists has been powerful. It's taken time, but it has broken through. And I think people now do realize that you need to listen to what science is saying.
Yes, I want to it's sort of in a related matter go back to your career in research at Oxford, and did you get to do a lot of teaching and writing when I mean obviously you published a lot of academic research, but did you do a lot of teaching or more general writing when you were at Oxford?
Oh, one of the joys of being a tutor at Oxford is that you spend a lot of time teaching. And that's the great blessing of being a student at Oxford, that you get taught by senior academics on a one-to-one or one with two students. And so it's a pretty heavy teaching load for half of the year. And in the early days, I found that quite a struggle to keep research going and to maintain my teaching as best I could. But I find teaching more and more rewarding as I find it satisfying to be able to transmit, help people to understand. Or as a famous physicist once said, Professor Zeeman, he said, I can give you an explanation, but an understanding you have to find for yourself. But I always found it a challenge to find the best way of explaining stuff to students. And I enjoyed doing that and I enjoyed getting feedback from students in that way. So I enjoyed lecturing and tutoring. And eventually I ended up writing a few textbooks based on my lectures. But generally speaking, I didn't have much time to write other books. If you're writing scientific papers, teaching and running research groups, as well as the other things you do, like raising children, and life is full.
Yeah, it's a lot to balance, and of course, writing grant applications as well, and
Yes.
doing conferences. And it sounds like you got to go all over the world. I mean, you got to go to some very interesting places. I loved your story about the Paris experiment. That must have been absolutely mind blowing. Who really inspired you? You've mentioned a few names of people that were important or leaned in on you, but who really inspired you at different points in your career and your childhood?
Oh gosh, that's a difficult question. There were so many, Sam, that it would be almost invidious to pick out a few individuals. I mean, I do owe a lot to my supervisor who got me started in research, Dan Bradley. He had a tremendous enthusiasm for physics that he transmitted to me as well. But so many colleagues with whom I've worked have helped maintain my momentum, and enormous respect and gratitude for my graduate students who did a lot of the nitty-gritty hard work. It was all very well for me to have an idea, but then to have someone come along and do the hard work of realizing it in the laboratory was great. And I've been privileged to work with some really very bright students who've gone on to their own academic careers, which has been very satisfying as well. So,
Famous names I can pick from you there. Any very notable people who you've had in your care who've gone on to do famous things?
well, again, that would be invidious for me to select a few of my graduate students because some of the rest of them said, "Why didn't you mention me?"
Yes, of course. Dangerous
But
game.
let me say, I've about half of my graduate students are now professors in some of the best universities in the country, from Oxford, Cambridge, Durham, London, all over the place. So they've done very well for themselves, and justly so.
Yeah, I think it is the wish, especially when you mention being humbled, which is a phrase you've used several times. You do wish that your students will surpass their master, and what a rich legacy you've had. I want to, before we finish, you did mention your Christian faith earlier, and that's quite interesting. I do want to ask about that because I know that later on in your career, you're quite involved with the Faraday Institute at Cambridge. Mm. Actually, I was with Dr. Dennis Alexander yesterday, as it happens, and a mutual friend of ours. Could you say something about the Faraday Institute and your work with the sort of the science and religion journals?
Yeah, well, my involvement with science and religion really started through Christians in Science, a separate organization that brings together scientists and people interested in the science religion area. And so a few years ago, they invited me to chair that organization, which I did for 4 or 5 years. And towards the end of that, then I was invited to join the Faraday Institute, which is an institute in Cambridge which focuses especially on the interaction between science and the Christian faith, or religion in general, but predominantly on the Christian faith. So it was a great privilege to go to Faraday and join them for a short time. A critical part in their development. So they do important work in bringing together young scientists and theologians to work on really interesting and challenging issues. For both Christians in Science and the Faraday Institute, one of our motivations has been to help the general public, children in schools and people in general, to overcome this very popular notion that science is some kind of obstacle to faith, that somehow you can't believe in science and believe in God at the same time, that they're mutually exclusive. When in fact the opposite is the case, that they're mutually enhancing, that actually what we know as modern science was nurtured in a Christian environment. And the whole notion that you could understand nature, that it made sense, comes out of an idea that the world was created by a rational God, when most religions don't have that idea, that early religions thought of nature as being random and chaotic at the whim of gods and capricious. So there's no point in trying to find any order in it, because inherently these gods just did what they want. And so the idea that the Jewish faith brought, that there was one creator, made help laid the foundation and made it reasonable to look for order. And as Johannes Kepler, the famous astronomer, said, the job of a scientist is to discover the order that has been imposed on nature by its creator. And so that's really what got modern science going in the Middle Ages. Of course, Greek ideas and some contributions from Islamic scholars fed into that. But it was really the Christian faith in the West that nurtured the growth of modern science out of medieval philosophy. That was based on the idea that God, the creator, had made the world and made us able to understand it. And there's some aspect of us that we're made in his image, so our rationality can make sense of the world around us. And so for me, that's one of the most powerful arguments, as it were, that sustains my faith, that it makes sense, that our rationality is derived from the mind of God in some way. And even our morality is derived from the character of God. And so it makes sense both from a logical point of view and from morality. It also makes sense historically, because the Christian faith and putting our faith in God has changed so many lives down the ages. And then finally, it makes sense to me personally, because as an experimental scientist, I find it works. You know, when I put my faith in God, I find that I've a spiritual strength and a peace that comes through living every day with God. And so I find it has changed my life enormously. And so it makes sense in all those four ways: logically and philosophically, morally, historically, and personally. And so they all come together. And I think that's what science demands of us, that scientific truth has to be coherent with other scientific truths. They must agree. And so truth, scientific truth, and Christian truth are coherent. And so they can't be in opposition to one another. And that's what we want to get across to people, and not to think that somehow science explains everything. There are things that there are limits to what science can tell us. It's enormously powerful and a great gift that we have, but it's not everything. And it points beyond itself, as it were, to some more deeper, ultimate purpose to life. Science can't uncover that, but it says, think of other ways of finding that out. And there are other ways. And through faith in God, we do discover that God is real. And so it all fits together. So that's one of the motivations for the Faraday Institute, both in its work in schools and colleges, and also to spread into the general public through churches, that religious people should not be afraid of science, but they should welcome it as a great gift of God and for the benefit of humanity. And people who are perhaps inclined to atheism, they shouldn't be afraid of faith either, because it's entirely consistent with science. So there's nothing to fear on either side.
This has been a big part of your later career and when you retired. And it's named after Michael Faraday, who was a physicist who had faith himself. Correct?
Well, he was indeed. He was a bit of a polymath, in fact. That's the coherent word to use in this context. I mean, Faraday was one of the greatest scientists who've ever lived, really. He contributed so
Yes.
much to chemistry and to physics. wonderful character.
Yeah, and so the Faraday Institute is sort of an academic research hub about science and religion that
Yes,
sort
yeah.
of sprung out of Cambridge University. Um, yeah, when I saw Dennis Alexander, who will definitely get on this show, incredible molecular immunologist himself. When I saw him last year, he mentioned in passing that on the physics faculty at Oxford University, amongst the professors, so not postdocs or PhD students, but on the professorship, there were 8 Christian physicists, including yourself. I thought that was amazing. I think many people would find that amazing and quite counterintuitive from the sort of the story we've had in recent decades about, or from the likes of Richard Dawkins, who I admire, but it would be quite shocking for people the average Joe on the street, perhaps, to hear that. So you were surrounded by Christians on the physics faculty, by the sounds of it.
Well, not exactly surrounded, but there were a significant number, much higher than the general population. The percentage of the physics faculty who were Christian believers was much higher than the general public. And that is an interesting phenomenon. And I remember, if you try to understand why that is, there's an interesting insight provided by a young man who was in Oxford at the time of C.S. Lewis was teaching there, a guy called Eric van Auken. And he was going around with some fellow students and noticing the same thing, that there were a number of scientists who were Christians. But he observed that most of them were physicists. And his explanation for this was that biologists realize that even if they don't have all the answers, the chemists, more fundamental science, they do. And so science can explain everything. Even if biology can't, chemistry will. And the chemists, they realized, well, no, it's not quite true, because below chemistry, there's physics. And so even if we don't understand everything, the physicists do. Well, physicists are actually dealing with the ultimate reality, and physicists know we don't know everything, and nor can we. And so they're generally more humble and open to faith in God, as it were. And I mean, they don't see science as being able to explain everything. And the faith in God is not an alternative explanation in any case. We're not offering a different explanation for things. We're offering a different perspective. It's explaining, if you like, on a different level. If you like, the why rather than the how of our existence. And
So
so,
it's not for you a case of we don't understand it yet, but I believe in God, so it's okay. Sort of God did it. Um,
oh
it-
no,
um,
we must never just use God as an explanation, because what God wants us to do is to use our brains that He's given us to find those explanations. If we find something we don't understand, we don't just wave our hands and say, "Oh well, God explains it." We try to improve our science to understand it better. All that will ever do is help us understand how the physical world works. It won't give us any clue as to the purpose of existence or its meaning. Science is not equipped to do that. Um, and we can work out so much using our reason, but reason will only take us so far. And it's an act of faith then to say that beyond that there's nothing. I think, in fact, it was Blaise Pascal who famously said that the supreme purpose of reason is to show man that some things are beyond reason. And put it in more quaintly, C.S. Lewis uses a little phrase where he says, "If reason cannot tell you whether the cat is in the linen cupboard, then reason itself will whisper, 'Go and look.'" So, there are different ways of finding knowledge, and science will tell us knowledge about certain things. Um, but scientific knowledge will never tell me whether my wife really loves me. I find that out by a different method, or whether I can trust my friend, um, uh, whether I can trust you, Sam, to tell the truth about what I've been saying. um, trust is something that develops in relationship with another being, another person. And that kind of trust also exists between us and God. And so we learn things about God by putting our trust in Him, just as we develop a friendship with another person by putting our trust in them. And that way we discover things about them that we would never know without that trust being put there in the first place. So there are different kinds of knowledge and different ways of acquiring knowledge. And science tells us one sort of knowledge, but our faith gives us a different kind of knowledge. And both are
That's
valuable.
very Yeah, it sounds like C.S. Lewis rubbed off on you a lot from your time in Oxford.
Well, actually,
What-
he lived just about a mile away from where I grew up in Belfast.
He was a Belfast guy, wasn't he?
Yes,
So you got the best of both fronts. So you're
yes,
sort of
yeah,
surrounded by
yes,
C.S. Lewis.
yeah. I
Yeah, I
suppose
love
that
C.S. Lewis too.
I should say then. You asked me who my hero was. It's C.S. Lewis. Okay, I learned so much from him. Um, and as a young Christian, where I was struggling with doubts about science and so on, he was enormously reassuring and convincing me that um, the Christian faith is a totally rationally justified belief, and I had nothing to fear from science. So he was enormously helpful in developing my faith.
I think Lewis died in '63, uh,
That's
if
right. Yes.
if I'm right. So there probably wasn't any crossover with you both. Did you ever see him in person? Oh,
Oh no, not at all. No,
no,
no. I was at school
even
when
with
he died.
Belfast and Oxford. Yeah, yes.
Oh, but
Yeah,
he
so
he lived
he
in
wasn't at Belfast at the time. No.
no, 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 no. He was in Oxford at that time, and in fact, he lived in a rather posh part of Belfast. I lived in a more working class part, so our paths would not have crossed.
No, well, that would have been something, wouldn't it? Um, Gosh. Well, yeah, I mean, we're about polymaths here, and it sounds like you've very much been a polymath in the both in the physics front and multiple subdisciplines of physics, but also the theology front. And it's always a pleasure to meet that. And it's certainly been a pleasure to talk to you today, Professor Ewart. Thanks so much for your time, and I really look forward to seeing you again, and hopefully getting you to inspire some of the students in my town as well.
Okay.
I got to say, it was such an honor to moderate a discussion on science and religion between yourself and Phil Halper, the science communicator at my old secondary school.
Yes.
And I do encourage people to check that out. If you're interested in a very high-end discussion on science and religion, do check that out. It's on Premier Unbelievable. Um, where can people find out more about your work or your writing?
Oh, um, well, I don't have a sort of personal website or anything like that. My mother instilled into me um, the notion that you should never put yourself forward or make an exhibition of yourself. And so I'm not prominent on social media or anything like that. But there's a website on the Oxford University Physics Department where you can find more about my physics work if people are interested. And so that, that that's probably the best place to start.
They should, and we really encourage students, young and old, out there who have an interest in some of the things Professor Ewart has talked about to, explore the frontiers of laser physics and atomic physics, and maybe to check out some of the science and religion research as well coming out of Faraday. Thank you so much for your time, Professor. It's been an absolute pleasure.
Thank you, Sam. God bless.